Number 21 here is introducing us to something called a logistic curve right here. And a logistic growth model is one that's far more realistic compared to polynomial and exponential growth models that we have. It happens very often in the natural world when we're talking about the population of a certain type of animal and ecosystem, or in this case, a sunflower here. So we're talking about growth that is very, very slow at the beginning. Then all of a sudden in the middle, growth really accelerates. But then towards the end, growth slows down a lot, and it almost levels off, meaning that this living object is barely growing at all towards the end of its life, or in this case, 100 days. So what are they asking us to do here, guys? They want us to estimate the growth rate at the point of inflection. So first thing I better do is try to figure out where that point of inflection is. And a point of inflection is the spot where your curve changes concavity. And it looks to me like at the beginning here, guys, this curve is concave upwards. Towards the end, it is concave downwards. And if I had to guess, that's all you can do right here, I would say that our point of inflection is right about that blue dot right over there, guys. Actually, my life might be a little bit easier if I actually figured it was right there. Oh, now I don't like what I did. Oh, dear God, it's getting worse. All right. Probably what I should have done is said, all right, get rid of that, get rid of that, get rid of that. Maybe life would have been easier if I said that was the point of inflection there. So POI, and I have to guess right here, guys, that is the ordered pair of 40, comma, and now somewhere between 100 and 150, I'm going to go with 140. Again, guys, we are estimating right here, so there's no real clear right answer to where that point of inflection is located. Now, they want us to estimate the growth rate. So this graph is measuring the height in centimeters of your sunflower over days. So your growth rate is going to be in the units of centimeters per day. What they want us to do here, guys, is estimate the slope of the tangent line right here at that point of inflection. Now to do that, to estimate the slope of a line, I'm going to need 2 points. Okay, so I've got this first point right here of 40, 140, and now I'm just totally taking a guess at a second point, but I see, maybe right over here. Looks like a decent second point right there, and it looks like that would be 20, and then let's see, our y-coordinate there looks like it might be close to 20 as well. So I'm going to go with those 2 points right there as 2 points that are located on my tangent line. So now to estimate the growth rate, again, this is just an approximation right here, we're going to find the slope of that tangent line right there. So it's going to be 140 minus 20. I'll go ahead and write that out all over, changing your x-coordinates, 40 minus 20. Okay, so that'll get us a 120 on top and a 20 on bottom. So it looks like our growth rate is about 6. And if we thought about units, the 140 and 20, those are measured in centimeters right there. And the x-coordinates, 40 and 20, were measured in days. Okay, so the unit that we have right here is 6 centimeters per day, and that is what our growth rate approximation would be at that point of tangency. So that's the first part of the answer to the question right there. But then they said, explain its significance. All right, so what's going on here, guys, is that at any particular point on that curve right there, you're going to get a growth rate modeled by the slope of a tangent line. So if I started right here, my tangent line would probably look something like that. And if I went a little further, my tangent line, my growth rate would probably look something like that. And if you look at those 2 green lines that I just drew and compare that to the line that I had in blue at that point of inflection right there, what we're dealing with at that point of inflection is the maximum growth rate here, the steepest that tangent line is ever going to get on this interval from 0 to 100. So when they explain this, they say explain the significance, that right there would appear to be the maximum growth rate. Okay, that is the time at which, or the rate at which, this thing is growing the fastest on the interval here from 0 to 100 days. So at that point of inflection, that's when this thing is growing as fast as it possibly would. If they wanted a sketch for the first and the second derivatives right here, let's see, h of t is what they call this function. So let me scroll down here a little bit. All right, there we go. So if they wanted a graph, let me move down here for h prime of t. Okay, what do we see when we look at that function here, guys? We start to see that our growth rate, modeled by the slope of our tangent, is pretty low at the beginning. Then it gets up to a maximum value of about 6, and then it starts to kind of level off again. So I would say that a approximate graph here for our first derivative would be something that starts low, gets high in the middle, and then kind of comes back towards 0 a little bit further on. And not that it really matters, but I think that that maximum growth rate right there we just came up with was going to be somewhere around 6, and I put that at 100 right over there. Okay? All right, so that's maybe a decent graph for what h prime of t might look like. And then h double prime of t, the derivative of the derivative, now they're asking us to model the slope of the tangent here. And it looks like we begin with a positive slope to this graph, then it's going to equal 0 right there in the middle, and then come down now, and it's going to be negative as we move off to the right. So my second derivative graph, the derivative of my first derivative, might start out a little bit positive like that, probably going to come down towards 0 and go underneath, and then end up maybe looking something like this. So that would be our guess right there as to what the second derivative would look like. Okay, so I think that's everything they asked us to find right there on problem number 21.